Alright, so in this video I'm gonna be explaining this important article with the title Recurrent Distance Filtering for Graph Representation Learning. So this important paper in 2024. Graph neural network based on iterative one-hop message passing have been shown to struggle in harnessing the information from distant nodes effectively. Conversely, graph transformers allow each node to attend to all other nodes directly, but lack graph inductive bias and have to rely on ad hoc positioning coding. So their approach stems from the recent breakthroughs in long-range modeling provided by deep state space models. So for a given target node, our model aggregates other nodes by their shortest distances to the target. So if this is a target node, it aggregates aggregates other nodes by shortest distances to the target and uses a linear RNN to encode the sequence of hop representations. The linear RNN is parameterized in a particular diagonal form for stable long-range signal propagation and is theoretically expressive enough to encode neighborhood hierarchy. With no need for positional encoding, we empirically show that the performance of our model is comparable to or better than state-of-the-art graph transformers on various benchmarks, with a significantly reduced computational cost. So if this is my target node, you see that, of course, there is a variation on this linear RNN, and it aggregates all the shortest passes between various neighbors that are far apart. So this is the idea. And then this is the sketch of your architecture that MLPs and layer normalization operate independently at each node or aggregated multiset. So information of distant nodes is propagated to the target node through a linear RNN. And so this is the architecture. We want to talk about the preliminaries first. That their shortest distance to node, our target node V, is just all the nodes that the distance, shortest pass is either, for example, N1 is when the distance is 1, N2 is like when the distance is 2. And now that you understand what is a neighbor of a node, for example, neighbor 3, it means that there are 3 hops to come, 1, 2, 3, to reach the target node V from node U. So there are 3 hops. And now that you know the aggregation, you aggregate like this. These are the type of neighbors that you are caring about. So K is important role. K plays an important role. This K, it shows how many hops. And the biggest one, of course, is the diameter of G. And then now that you aggregate all of these things, so it's a multiset, and AGG is an injective multiset function which is parameterized. So we can this reference represented this by some MLPs. But these set of representations naturally form a sequence according to the shortest path. So we encode them like a linear RNN. And S represents the hidden states of the RNN. So with probability 1 over random initializations, A is diagnosable, and lambda, the diagonal matrix, gathered the eigenvalues. So we can represent it like this in a better form. So we unroll the recurrence. So this equation can be thought of as a filter over the hops from the target node. And the filter weights are determined by the magnitudes of eigenvalues lambda. So the output representation is generated by a nonlinear transformation. And you can compare it for different data sets like MNIST, CFAR10, cluster, and different models, the typical graph convolution or graph attention. And this proposed model, you see there is an improvement for graph attention, 3% for MNIST. And for cluster, it's even bigger, 9%, 8%, if you compare it with graph attention. Of course, graph attention, you see, is 1% better than graph convolution because of that attention on the edge. But this one is a big improvement. This one is a bigger improvement. So that's interesting that it can beat graph attention. So interesting.